See the next problem of, right, next problem on Dijkstra's algorithm. See this. Next problem on Dijkstra's algorithm. Now see this one. If you see this problem carefully, you will see one interesting thing. What is that? See this problem. Two examples I said. Mostly they are more than enough. Right? Let's see anyhow third problem. See this. If you see this problem, you will see one interesting line. What is that? Can you help me? It is a weighted graph or unweighted graph? This graph is, I am not asking directed or undirected. It's a directed or undirected. It is a directed, that is okay. But the weighted or unweighted means weights are there or not? Yes, weights also there. But it is, you see this one, if you observe clearly, right? Previous two problems if you observe, right? So in the given graph, all edge weights are positive in the previous one. Now in this graph, right? Some edge weights are negative. Check. Some edge weights are negative. C2B. Some edge weights are negative. So I think that is a specialty with this problem. If someone asking you in the third problem what I am going to explain, if the graph contain negative edge weight, some positive also may be there, some negative there, if graph contain negative edge weights, right, how to find out single source shortest path, right, I will explain now, right, I will explain. Please be careful. If the graph contain negative edge weights, how to find out single source shortest path? From this problem I will explain. Let me check here. Let me check. So using Dijkstra's also I will do, right? But before going to that, let me do manual checking. Manually. Suppose in that I don't know any algorithm. How to find out? To this problem, how to find out single source shortest path from the source A, right, source A to every other vertex, how to find out single source shortest path in the given graph where negative edge weights are there. Few may be negative, right? How to find out I will explain. Afterwards we will go to the algorithm, right? Maybe Dijkstra's will do that. See this one. You please verify yourself. A to A how much? Source is A to A how much? A to A 0, that's okay. Because no one can come back to A. Please see this. Only one chance, A to A 0, that's okay. Can you help me know what is A to B? Just to do manually, there is no algorithm here, within few minutes I will do that. So can you help me now, right? So A to B how much? I want shortest path, A to B. Can you help me now? To come to B, how many people can come? I want to go A to B, that's okay. How many people can come to B, right? How many people? I think A to B directly you can come here. You can go A to C, C to B also. Can you help me now? If you go A to B directly, how much? 10. If you go A to C, C to B, how much? 50 minus 45. What is the answer? 5. Some people are thinking that to go from A to B, best answer is 10. No. Right? To go from A to B directly if you go 10, via C if you go 50 minus 45. I think 5 is the answer. Some people are thinking that A to B if you want to go 10, one answer, one more is 50. See, one answer 10, one more is 50 plus something, that something is minus 45, which will goes to 5. So A to B 5. Can you say what is the A to C? To come to the C, one way is directly come 50. One more, go to B and come back. Can you help me now? To go B how much? 5. 5 plus 60, 65. To go to A to C, one is directly come 50. One more is go to B first. Already B how much? 5. Already B 5. 5 plus 60, 65. I think 50 better. A to C 50. Let's go to the A to D. Let's go to the A to D. What is the answer? A to D. Can you say who can reach the D? I think B also, C also. To go to the A to D, one is go to B from there. What is the B value? 5. 5 plus 7, 12. One more is go to C. C already 50. 50 plus 9, 59. Can you help me now? 5 plus 7, 12. Right? 50 plus 9, 59. Which is better? 12. 12 better. So to this problem, listen, to this problem, from source A to every other vertex, cost of the shortest path is going to be this one. The specialty about this problem is going to be, if graph contain negative edge weight, right, how to solve it? What are the implications going to be happen? Right, we will see now. What are the implications going to be happen? We will see now. So I am thinking that manually I done here, no logic, nothing I applied. That is the meaning of manual checking. Manual checking means manually I am trying. Right, using Dijkstra's algorithm, I will try the same problem. You know Dijkstra's very well now, right? Let me do Dijkstra's. Using Dijkstra's algorithm, this problem how solve, right? Let's check. See this one, Dijkstra's. You know very well, same thing I am doing. Using Dijkstra's. Can you help me know what is the first one? Present in min heap. You know very well, that is the reason I am saying present in min heap. A, B, C, D. A, B, C, D. Next one. So because of A is source, 0, null, infinite, null, infinite, null, infinite, null. Dijkstra's present in min heap, A, B, C, D, right? These are the vertices, right? A is the source, 0, null, infinite, null, nothing special. Positive, negative doesn't matter. Dijkstra's algorithm already you know. Just apply blindly Dijkstra's algorithm. And one more, don't try, not required of time complexity and all. You know time complexity of Dijkstra's very well. No need to write every time. You know very well time complexity. What is the requirement of writing again? Right? Not required. Time complexity, so don't worry. So let me write here. I think everywhere two values. Minimum parent. Because of the source, 0, null, infinite, null, infinite, null, infinite, null. Simple Dijkstra's. Whatever you know, that only I am doing. Can you help now? Don't write time complexity little bit also. See this one. Right? Delete. A is came out. Dijkstra's algorithm, simply Dijkstra's algorithm. A is deleted. Can you help me what he will do? A is deleted. Yes, as soon as you will delete, you will go to adjacency list, you will ask, who are there adjacent? Who are those? B and C. Those two places try to do decrease key operation. What is the answer? Right? 0 plus 10, 10. From where? A. One more. 0 plus 50, 50. From where? A. It's two people. Let me write now. What is the B now? 10A. What is the C now? 50A. What is the D now? Infinite null, like this. Now can you help me? If you delete now, who will go out? B. If you delete now, B will go out. Now can you help me now? See this one, after A, B deleted. Yes. Can you help me? As soon as B is came out, what he will do? Right? B will find out all B adjacent people. Can you see who are the B adjacent people? B adjacent people are C also, D also. I think two people. B adjacent people are going to be B also, C also. B adjacent people are going to be C also, D also. Let's do decrease key operation there. So what is the answer? B already 10. 10 plus 7. What is the answer? 10 plus 7, 17. From where? B. One more. Right? Already B value 10. 10 plus 60, 70. But I think 50 better, no change. Two places I done decrease key operation. One changed, one not changed. It's okay. So let me write the B. After completion of B, let me write the answer. Can you help me know what is the B now? Sorry, what is the C now? What is the C now? 50A. What is the D now? 17B. Right, like that. If you delete now, you know Dijkstra's algorithm, same thing. Don't worry, little bit also about negative, positive. Don't worry. Let me delete now. What is the answer? D came out. Now one more thing I want to ask. After B, who deleted? D deleted. After B, D deleted. Can you help me one small note? D deleted. What the D will do? D will find out adjacent. Is there any adjacent? No. So because of no one is adjacent, same thing will come. Next one. Delete this also. Who deleted lastly? C deleted. Can you help me know who deleted first? A. Y is best. Next who deleted? After 0. A is 0. After 0 who is the next best? I think 10. After 10 who is the next best? 17. So this one. See everyone listen. First minimum deleted. Next minimum deleted. Next minimum deleted. I think last one I am deleting C. See this one. Why is C deleting lastly? What is the reason? Comparing other people. C value big. See this. Why A deleted first? A is 0. Why B deleted next? After 0, 10 minimum. Afterwards, why D deleted? 17 minimum. Right? After D, why C deleted? I think after 17, next minimum is this. Why C came late? Comparing other people, he is bigger. That is the reason he came late. Please be careful. C came late. What the reason is? The reason is comparing other people, C value bigger. That is the reason he came late. Anyhow, C came as usual. C deleted. That is okay. After C deletion is over. Can you see who are the C adjacent? See in the graph and talk. Who are the C adjacent? C adjacent is going to be, listen, C adjacent is going to be B and D. C adjacent is going to be B and D. C is came late, that is okay. C adjacent is going to be B and D, that is also okay. But one thing I want to ask you, C adjacent is B and D. C adjacent is B and D, right? You know this very well. C adjacent is B and D. And one more, they are already over or not? They are already over. C adjacent is B and D, they are already over. Why they over? They are minimum, that is the reason they are over. So C came late and C adjacent is B and D, they are already over also because they are far better than C. That is the reason they over. They over, they deleted from min heap also. They deleted from min heap also, right? Please be careful. Now some people are asking, if they are already over, can't I do decrease key operation? How can you do? Because they are not in the min heap. If they are not in the min heap, how can you do decrease key operation again? Some people are asking, sir, why they are not in the min heap? They are already minimum. They are already minimum. Comparing C, they are already minimum. How you only say how bigger person can change the smaller. How bigger person can change the smaller. That is the reason, right? A is minimum, delete. Next B minimum, delete. Next D minimum, delete. Afterwards C came, C next minimum, right? C deleted is okay. But C adjacent is B and D. They are already over. If they are already over, no need to do decrease K operation there. What is the reason? They are already over. Right? Some people are asking, sir, can't I do decrease K operation? If you want to do also, they are not in the min heap. They are not in the min heap. We deleted already. So that is the reason. If you want to do also, not possible because they are not in the min heap. The reason why we deleted is they are already best too. That is the reason we deleted. But see the interesting thing. Even though, listen, comparing the ABD, this C even though worst one, right? So because of he came, what is the reason why he came late? He is bigger. That is the reason he came late. They are already smaller people. They are already deleted also. This bigger person, how they can change the smaller one? That is the reason in the Dijkstra's algorithm, smaller delete. Because afterwards big people will come. That bigger one cannot change the smaller. Because smaller people are already better, they deleted. How the bigger person can change the smaller? But interesting thingy, even though C is bigger, these are smaller. C can change the bigger. Some people are asking, sir, how? Right? How it is? See this one. 50, C value 50 already. 50 minus 45. See this one. C value already big. 50 minus 45, 5. Right? 5. I think see this one. It is a 10. This value 10 only. Very small. C value 50. That is very big. How bigger person can change the smaller one? Right? So, in the case of the Dijkstra's algorithm, try to remember, right? Bigger person cannot change the smaller one. That is the reason. Smaller delete. Please be careful. Right? But negative is there. Please be careful. Bigger person can change smaller also. But Dijkstra's algorithm don't allow. What is the reason? Dijkstra's algorithm is meant for positive edge weights only. If negative edge weights are there, Dijkstra's algorithm may fail. Please be careful. Some people are asking, sir, why Dijkstra's algorithm may fail if graph contain negative edge weight? If you want, you can see now. Can I help you now? So A is out, A deleted. According to Dijkstra's, we are doing Dijkstra's algorithm. Forget about negative, positive. A minimum, delete. Next one B minimum, delete. Next one D minimum, delete. Now C is came now. See the answer. Now C is came now. C adjacent, B and D. C adjacent is B and D. They are already over or not over? They are already over. According to Dijkstra's, if they are already over, don't do again. If they are already over, don't do again because they are not in the min heap. So, but one thing, if you don't do, according to Dijkstra, they are already over, don't do. Right? If you don't do, what is the problem? 50 minus 45 is going to be 5. Right? The actual answer is 5, but Dijkstra is saying that they are already over, don't do. Because of that reason, this is fail. Can you help me now? C adjacent. Let me do the Dijkstra's. Forget about right answer, wrong answer. So, C is came out. Yes. C adjacent is B and D. Yes. Those two places I want to do decrease key operation, but they are already over or not? Yes. If they are already over, no need to do. According to Dijkstra's, they are already over, don't do. But because of negative, you have to do also. But Dijkstra is meant for only positive. If you give negative, it is your problem. Please be careful. So Dijkstra algorithm simply saying that I constructed this algorithm by thinking that practical things only. Dijkstra is simply saying that I constructed this algorithm by thinking about positive edge weights only. Right? Practical things only. What is the meaning? Practical thing means what? To go from one city to another city, it will take some cost. It may take 20 rupees, it may take 50 rupees, but it cannot take minus 10 rupees. Please be careful. Practical single source shortest path algorithm is the Dijkstra's algorithm. Dijkstra thinking that all positive only will come. See, if at all positive will come, that bigger person cannot change smaller one. Some people are asking how, right? If at all are positive, you only say C came late because he is bigger, right? How the bigger person can change smaller? You only say if all positive, 50 plus something is more than 50, how it can be 10? So positive, Dijkstra's algorithm will always work. Negative, Dijkstra's algorithm may work, may not work. Some people are asking, negative means Dijkstra's will fail every time or sometimes may fail? Maybe sometimes fail. Need not be every time, sometimes. Some people are asking how, right? How? Let me check here. Listen, let me check here. See this one, 50, careful listen, 50 minus 45, right? What is the answer? 5. According to Dijkstra's, don't change, but I have to change. 50 minus 45 is 5. I have to change, but Dijkstra is saying that I don't allow because he is already over. So, for this problem, Dijkstra's may fail. For this problem, Dijkstra will fail. What is the reason? 50 minus 45 is 5. I want to change, I cannot change because Dijkstra is saying that if already over means I don't allow. Now, okay, some people are asking, sir, when, even though negative there, when Dijkstra's will pass, if you want you can check, it is a 50, it is not minus 45, it is a minus 5, we assume that minus 5. Can you help me? 50 minus 5, what is the answer? 45, but 10 is better. Dijkstra also saying 10, right? By adding negative also 10 only better. Try to remember this. See this one. Can I change this one or not? It's actually according to Dijkstra's, right? Bigger person cannot change smaller. Because of that reason, right? He already deleted also. Because of negative, I have to change also. But Dijkstra saying that I don't allow. So Dijkstra's fail, graph contain negative. Need not be every time, sometime. So this is the case where fail will happen. Dijkstra saying that I don't change. Dijkstra is saying that C plus, that C means 50. 50 plus minus 45 is 5. So Dijkstra saying that if is it 5 or 10, 20, I don't worry. I don't change because if already done, I don't do. If already done, I don't do. Right? If you don't do, there may be a problem. 50 minus 45 is 5 because of you are not changing, Dijkstra's will give wrong answer. But negative doesn't mean that Dijkstra's will always fail. Maybe sometimes. Some people are asking, give one example where even though negative, Dijkstra's don't fail. Assume that it is not minus 45. It is only minus 5. You only say. According to Dijkstra's 10 better. What are the 50 minus 5? 45. 10 only better. Anyhow, Dijkstra's don't change. It is the 45. If at all it is a minus 5. 50 minus 5 is 45. But Dijkstra saying that I don't allow, 10 is better. So I think it is the last time I want to ask you. Please listen. Please listen. Dijkstra's algorithm is meant for positive edge weights only. If negative, Dijkstra's algorithm may fail. May fail, right? So what the Dijkstra's will do normally? If someone already over, don't do it again. Can you help me? Who over first? A, next to B, next to D, lastly C came. Right? C adjacent is two people who are already over. Because of they are already over, whether it is coming less or more doesn't matter. They are already over, don't do anything. Can you help me now? C adjacent, B and D, they are already over. Yes, don't do. Wrong answer, right answer doesn't matter, right? Already over means don't do. C adjacent is two people, they are already over, don't do it, stop it. So this is the Dijkstra's algorithm answer. You know Dijkstra's answer very well, right? Dijkstra's algorithm very well you know. Take minimum, adjacent people who are not completed do. A adjacent people B and C not completed do. Yes, I done. Next one, minimum is B. B adjacent which are not completed do. If completed, don't do. Next one, D adjacent, right? Is there anyone? No. C adjacent, B and D, but they are already over, don't do. It is the right answer, wrong answer doesn't matter. If they are already over, even though adjacent, they are already over, don't do. So Dijkstra strongly believing that, right? Bigger person cannot change smaller. Bigger person can change sometimes smaller also, but still Dijkstra's don't bother. When it is, if the graph contain negative edge weights, anyone can change anyone. If graph contain negative edge weights, anyone can change anyone. But Dijkstra is meant for positive edge weights only. If we give negative, Dijkstra's may fail, may pass. One example for fail, this is the example. Right? Actual answer is, right, to go from C to B, C 50, 50 minus 45 is 5, but Dijkstra is not taking. Now can you help me now to this problem? According to Dijkstra's, what is the answer? Let's check. To this problem, according to Dijkstra's, what is the answer? I am verifying. How it is? Can you help me? How it is? A value. What is the answer? 0. Manually I done already. Safe side. To verify. Can you help me now? So what is the source to B? 10. See this one. Actual answer is 5. But Dijkstra don't bother at all. He will do simply one scan. Dijkstra's will do simply one scan. It is the right answer, wrong answer, he don't care. If already over, you don't do it. Even though wrong, he don't bother. He is not interested answer. He is interested process. Whatever you done for the previous two problem, this problem also do same. Even though wrong answer. Because of negative, wrong answer may come. I cannot change the procedure. Negative one way, positive one way, Dijkstra's don't do. Algorithm means it is a fixed do. According to this algorithm, whatever you done previously, do same. Actually 5 is expected, but Dijkstra is given 10. What is the reason? Someone is already over. According to Dijkstra's, you don't do it again. Because of he is not doing again 10 coming, but actually 5 required. So this is fail. Can you help me now? According to Dijkstra's algorithm, what is the source to C? 50. Manually also 50 came, no problem. Next one. According to Dijkstra's algorithm, source to D 17. According to Dijkstra 17. But actual answer is 12. It is also wrong. Right? It is also wrong. Some people are asking, sir, how it is wrong? Let me check here. How it is wrong. Can you help me one small line? Who are the C adjacent? You only say, who are the C adjacent? C adjacent is B and D. They are already over. That is the reason Dijkstra's don't do. But actually you have to do because of this negative. But Dijkstra don't bother about positive and negative. Right? Simply you will see. They are already done or not. Yes. Right? Even though C is saying that I want to go and I want to do. But Dijkstra saying that they are already done, don't go. But actually you have to go, right? Then only you will get correct answer. But Dijkstra saying that I don't worry about the correct answer or wrong answer, right? According to my procedure, already over means don't do. Suppose that if you go, what will happen? Let me check. What is the answer? 50 minus 45? 5. It is a 5. So it is a wrong. Dijkstra saying don't go, but actually here 5 is coming. You have to take, but Dijkstra not taking. So Dijkstra wrong here. And one more. If it is 5 plus 7, 12. This is also wrong. If someone is this one, because of it is wrong, right? Wrong plus something, it is also wrong will come. So that is the reason 2 wrongs came. So B also wrong came, D also wrong came. What is the reason? So actually we should allow this person to change. But Dijkstra saying that he is already out. I cannot do anything here because he is already completed. Actually 5, but Dijkstra saying that it is already 10. It is already over also. I cannot change. So it is wrong. Wrong plus something. It is also wrong. That is the reason 2 people became wrong. Right? So just to explain, listen, what is the thing I done until now? Until now, see this one. Until now I done manually and Dijkstra's also. What is the reason? I want to say that Dijkstra's fail if the graph contain negative edge weights. To say this point only. What is the reason? Right? Because of negative, right? Definitely, even though he is the bigger person may change, right? Already completed people. Because of negative, right? Bigger people may change the smaller people also. But Dijkstra, don't worry about, right, negative, positive and all. He will simply follow his logic. What is that? If it is a bigger, already completed people, you cannot do anything. They completed, why? They are smaller. How bigger person can change the smaller? According to Dijkstra's, it never happened. Why? Dijkstra thinking always positive will come. So according to Dijkstra's, right, this is the answer. Actual answers are these. I think 2 people got the wrong answer. Don't give blindly. Dijkstra always give wrong answer. If the graph contain negative and all, don't do like that. Don't do like that. Right? Graph contain negative. Dijkstra's may fail. Give one example where Dijkstra's don't fail, even though graph contain negative. Just give here minus 5. If it is a minus 5, see this one. Already these are completed. Right? This is 50. 50 minus 5. What is the answer? 45. Dijkstra also saying 10 is better. Right? So I think now also same. Right? 10 only better. So that is the reason. Negative doesn't mean that fail. If negative there may fail. How it is fail? 50 minus 45 is 5. I want to change. Dijkstra saying I don't change. This is the place fail. Right, next one. If it is a wrong plus something also wrong. That is the reason 2 wrongs came. The purpose of this entire explanation, whatever done until now, right? Whatever I done until now, right? So just to explain, if the graph contain negative, Dijkstra's may fail. Simply do whatever you done for the previous 2 problem, just to do like that Dijkstra. Don't try time complexity every time. Don't try. Just to do Dijkstra's, these are the Dijkstra's answer. Manually I done, compare both of them. Whichever places fail, that is fail. Suppose if you don't want to do manually, see this one. They will give one graph and they will ask you, right, in that graph positive, negative both are there. They will ask you if you apply Dijkstra's algorithm, to which vertices wrong answer will come. They will ask you. Don't say blindly, this will give wrong, this will give right like that. Don't say anything like that. Right? Then what will you do is this one. If anyone asks you using Dijkstra's on this graph where positive, negative is there, which vertices right answer will come, which vertices wrong answer will come. If they ask you, just to do like this. Right? Don't do manual checking also. If you do manual checking, if you do this, it will take a lot of time. So best idea, don't do manual checking also, right? Just to do only Dijkstra's. Just to do only Dijkstra's. Listen, just to do only Dijkstra's. Whatever Dijkstra's say, follow like that, right? At some point of time, what happened? Right? So I am at C, See correctly now. This is the only thing what you have to take care. Just to do only Dijkstra's, right? Minimum delete, adjacent do. Minimum delete, adjacent do. Like that. So I deleted minimum. I deleted minimum C. What is the C adjacent? C adjacent is going to be B and D. C adjacent is B and D because of they are already over. Because of they are already over. Dijkstra saying don't go. Dijkstra saying don't go. But because of negative, you have some doubt on the Dijkstra's. Dijkstra saying that they are adjacent but they are already over, don't go. But you have doubt on Dijkstra's, right? Even though Dijkstra saying they are already over, don't go. You go and verify, don't change. You go and verify. So I am at C now. C adjacent is 2. They are already over. Dijkstra saying that don't go. But because of negative, I have doubt. Dijkstra saying don't go because they are already over. Because of negative, I have doubt. So I will go and I will verify, but I don't change. So I am at C. C adjacent is 2, right? Because of they are already over. Dijkstra saying that don't go. But because of negative, I have doubt on Dijkstra's. I will go and verify. How? Let's check here. What is the 50 minus 45? 5. So I took and I verified 5 is coming, but it is a 10 according to Dijkstra's, right? Actually 5 coming. So this is wrong. I don't change, but I want to know which will give wrong. So Dijkstra saying that don't go because he is already over. Because of negative, just go and verify. Right? If it is positive, no need. If it is positive, no need. Can you help me now? C adjacent is B and D. C adjacent is B and D. So Dijkstra saying that he is already over, don't go. Dijkstra saying that he is already over, don't go. Because of positive, whatever he is saying, listen. Whatever he is saying, don't listen. Dijkstra saying that he is adjacent, it's okay, but he is already over, don't go. Because of positive, don't go. No problem. Next one. So C adjacent is B, because of it is already over, Dijkstra say don't go. Because of negative, you have doubt on Dijkstra. Even though Dijkstra saying don't go, because of doubt you are going and verifying. 50 minus 45, 5, but it is 10. So this is mistake. But don't change. You are doing Dijkstra's only, but you are verifying. Is it mistake or not? Yes, mistake. Dijkstra saying don't go, you have doubt, you went and verified also. 5 required, but Dijkstra saying 10, this is wrong. When you say it is wrong plus something also wrong, there may be chance. 5 plus 7, 12, but it is a 17, so 2 places wrong. Everywhere, listen, everywhere, Dijkstra saying that positive, negative. See this one, graph contain positive also, negative also. You want to check if you apply Dijkstra's, which vertices Dijkstra's will give wrong answer. Then what is the answer? Don't do manual checking. For your convenience, I explained. In exam, don't do manual checking. Just to do simply Dijkstra's. Whatever he is saying, just do that. At some point of time, at some negative, whenever negative edge weight is there, that time just behave like that. Dijkstra's will say, for the C, B adjacent, but he is already over, don't go. Because of negative, you have doubt on Dijkstra's. Even though he is saying don't go, you go and verify, don't change. You go and verify. After verifying, you got to know it is wrong. Don't change it, it is wrong. If it is wrong, just note it down. Okay, Dijkstra's for this person, wrong answer coming. Because of he is wrong, on him, if anyone depending, that person also may be wrong. Right? Like that, you have to verify. So same way I verified. See this one, same way. Here, see this one, whatever he said, I done. Because of see, nowhere negative came. Now I am at here now. So C adjacent is going to be B and D. So Dijkstra saying that is already over, don't go. Yes, I didn't went because it is a positive. Positive means Dijkstra's right. Next one. So I am at here now. C adjacent is B is already over. Dijkstra saying don't go. Because of negative, I have doubt. I will go and verify. So 50 minus 45, 5, but it is a 10. So I think wrong is there. You confirm, but no need to change because it is a Dijkstra's. You have to follow whatever he is saying. Doubt there, go and verify, but don't change. So it is wrong. Wrong plus something, this is also wrong. Like that you have to check. Right? Don't do manual checking, it will waste lot of time. Now final conclusion I want to say to you. See this one. See everyone. Dijkstra's algorithm will give always correct answer when if the graph contain all positive edge weights. If graph contain negative, Dijkstra's may fail. To give the clarity, I explained manual checking, I explained the Dijkstra's algorithm also. If you want, you can verify. A, manual also 0, Dijkstra's also 0. B, manual is 5, but Dijkstra's is 10. So this is the place where Dijkstra's fail. C, manual 50, Dijkstra's also 50, no problem. D, Manual is 12, Dijkstra's is 17. Manual is 12, Dijkstra's is 17. So Dijkstra's failed here also. Two places it failed. So because the manual checking is there, you are comparing like that. Without this, how will you check? Same way. He will say, if negative is there, he will say, is already over, don't go. You have doubt, go and verify. You got to know 5 is the answer. But Dijkstra saying 10 is the answer. So it is fail. Fail plus fail, it is also fail. Like that you have to verify. So from this conclusion is going to be, if graph contain negative edge weight, Dijkstra's algorithm may fail. Means some doubt there. From today onwards, if I give negative edge weight graph, a graph which contains few negative edge weight, what is the dilemma we have? A graph which contains some negative edge weight, the dilemma is going to be, Dijkstra's may fail. When you know that you have dilemma, why you apply that algorithm? When it is confirmed, all positive, Dijkstra's always correct, please go ahead. By seeing graph, okay, all positive, Dijkstra's always correct, go and do that. If graph contain negative, it may fail. If it may fail, some doubt is there, what is the requirement of doing that? There is a one algorithm, even though graph contain negative edge weights, that algorithm will give always correct answer. That algorithm name is called as Bellman-Ford algorithm. The purpose of this problem, just doing Bellman-Ford algorithm. Graph contain negative, how to do Bellman-Ford algorithm, I will explain now. Right? I will explain. See this one, Bellman-Ford algorithm. The purpose of this problem is Bellman-Ford algorithm only. Please be careful. I am explaining now. Same problem, everything same. Bellman-Ford algorithm, how? I will explain. It is very simple. Comparing with the, right? See this one, comparing with the Dijkstra's Bellman-Ford algorithm is very simple. Bellman-Ford is meant for positive also, negative. Positive also it will work. Negative also it will work. Right? Same graph. Let me take same graph. Let me take the same graph. Graph contain positive, it is a 7, it is a 9. It is a given graph. So Bellman-Ford algorithm we have to do, right? I will do now. What is the procedure for this? What is the procedure for this? It is entirely different. Just see one time. Just see one time. See everyone. How to do Bellman-Ford algorithm on the given graph which contain combination of positive and negative. See, this is the way. As usual. See this one. As usual. Make sure that everyone listen. As usual. See the answer. Minimum and parent. Two values. Two values required. Let me write. Minimum and parent. Same. As usual. Like Dijkstra's. Let me write. Minimum and parent. Here also minimum and parent. Minimum and parent. So like that, so just write all as usual. Because of is the source, 0 null, infinite null, infinite null, like that write. Right, that is also okay. Right, fine. And until now I am thinking that you are really comfortable. But one small story there, right? I will say that line, right? I will come back. Please careful. One small story there, just I am saying now. This is very important one. To this algorithm, this is the major one. Just listen. Just listen. One small story I am writing here. Right? One small story I am writing here. Just listen. One small story. See the answer. See. Find at A completed. Then we can say relaxation at A completed. Let me read it. Let me read. Find adjacent vertices of A and perform decrease key operation on those vertices. Then we can say relaxation at A is completed. Please be careful. This is the definition. Relaxation at A is nothing but, what is the meaning of relaxation at A? A adjacent vertices you find out. Right? Suppose that A adjacent people are, assume that B, C, D. First to find out A adjacent people, B, C, D. Right? On B, C, D. On B, C, D, perform decrease key operation. Suppose assume that you done that also. Then I can say that relaxation at A is completed. Relaxation at A is completed. Right? Please be careful. Are you okay with that? If you are okay, see this one. If you are okay, please listen. I am thinking that you are little bit comfortable. See this one. This line is you are okay. Relaxation at A is completed. That is fine. See the next one. See the next one. One more point. This is one point assume. See the one more point. One more point. In Dijkstra's, every vertex relaxed only once. In Dijkstra's, every vertex relaxed only once. It is the second point. In Dijkstra's, every vertex relaxed only once. Third point. See the third point. In Bell-Manford, every vertex relaxed v minus 1 times. So these are the 3 points which required. So I'm reading all of them, right? I'm reading all of them. See, for Bell-Manford algorithm, I want to explain Bell-Manford. I remember that to explain Bell-Manford algorithm, right? These points required. I written on the board also, these points required. Can you see the first point? Find adjacent, see this one. To explain the Bell-Manford algorithm, right? We need few things. Those I written on the board also. I will read once. Please listen once. Please listen. See this one. First point. Find adjacent vertices of A and perform decrease key operation on those vertices. Then we can say relaxation at A is completed. That is the first thing. So what is the meaning of first point? At A, see this one. What is the meaning of relaxation at A? I am explaining. Relaxation at A is nothing but A adjacent people find out. Assume that BCD. At the BCD, perform the decrease key operation. Then I can say that relaxation at A is completed. That is the first point. In the case of Dijkstra's, right? At every vertex, relaxation will be done only once. But in the case of the Bell-Manford, at every vertex, relaxation will be done v minus 1 times. Right? These are the 3 points. Now, if anyone not okay with the first one, let me check here. First point, second point, let me check here. See this one, Dijkstra's. See the Dijkstra's now, what happened? See this one, as soon as A deleted, careful listen. As soon as A deleted, see this one, as soon as A deleted, what you done? See this one, as soon as A deleted, what you done? A adjacent people you find out. Who are the A adjacent people? I think B and C. A adjacent people find out. Those two places do decrease key operation. See, here also decrease key, here also decrease key. Right? See this one. As soon as A deleted, it's okay. Right? A adjacent find out. S2 people. Those two places do decrease key operation. SC done. Then I can say that relaxation at A completed. So A completed. That is the meaning. A completed means relaxation at A is over. Next one, B complete. Listen everyone now. B relaxation is over. What is the meaning? B adjacent find out. Those two places perform decrease key operation. Then I can say that B relaxation also over. Next one, D relaxation also over. Afterwards, C relaxation. Can you help me one small line now? Who relaxed first? A in the Dijkstra's. Next B. Next one D. Right? So like that. And one more thing. A relaxation is over. B relaxation also over. D relaxation also over. But do you believe or not? You cannot relax A again because A deleted. You cannot do A relaxation again because right A is already deleted. That's what the second point is saying. See the second point here. What is the meaning of relaxation at A? I explained to you. Next one. In Dijkstra's, every vertex relaxed only once. But in Bell-Manford, many times will be relaxed. How many times? V minus 1 time. Please be careful. Whatever you know, that only some technical word they kept. So, see this one. I think as soon as A is came out, A adjacent people find out. Those places do decrease key operation. This total story is called as relaxation at A. In the case of Dijkstra's, every vertex will be relaxed only once. You cannot relax again. One time only you have to do. Next one, in Bell-Manford algorithm, many times you will do. How many times? V minus 1. Right, V minus 1. I'm thinking that you are really comfortable. Right? Fine. Let's see this one. Because of you are okay, let's see this. See everyone now? I think everything is clear. First step, in Dijkstra's algorithm, first step. For everyone, keep the minimum parent. Right, is I think source is going to be 0 null, remaining is infinite null. That is also okay. Now see the answer. If from now onwards, if anyone asks you, right, on this graph, apply Bell-Manford algorithm. First keep like this, yes, you kept, and one more. After keeping, just can you count here? How many edges are there? Count. First step, see this one, forget about, see this one. If from now onwards, if anyone asks you Bellman-Ford algorithm, don't do before. Don't do those also. Don't do those also and don't do before also. Just to do only this. To explain this one clearly, maybe I said something before. Maybe I am saying something afterwards also. But concentrate here only. First step. Right? At every vertex, keep two values. Minimum parent. For all of them infinite null, for the first one 0 null as usual. Second step, see the second step. After doing that, second step is going to be, careful listen, right? How many edges are there? Count. Let me give edges. 1, 2, 3, 4, 5, 6. 6 edges are there. So second step of the Bellman-Ford algorithm after this is going to be, for every edge give number. See this one, it is the edge number 1. You can give any order, edge number 1. It is the edge number 2. It is the edge number 3. It is the edge number 4. It is edge number 5. It is edge number 6. Right? On this graph. So, how many edges are there? For all edges, give number. You give whatever order you like, no objection. Edge number 1, edge number 2, edge number 3 for all edges. Can you help me now? Can you help me now? Who is the edge number 3? This is edge number 3. What is that? B to C. Can you help me now? Who is the edge number 2? C to D. Edge number 1, B to D. Edge number 6, A to B. Edge number 5, A to C. Edge number 4, C to B, like that. Just give edge numbers. Minimum parent you write, that is okay. Next one, give edge numbers, whatever order you like, that is also okay. After writing that, careful listen, after writing. See everyone, interesting one. So, Bellman-Ford algorithm, see the answer. After doing that story, see the Bellman-Ford algorithm. Vertices, all vertices you take, A, B, C, D. All vertices you take A, B, C, D, and one more. What should I write here? Previously I written present in min heap. Now here, see this one. Not present in min heap, present in array. Not min heap, it is an array. Please be careful. What is the reason? I will explain afterwards. Present in array. Those vertices are A, B, C, D. I think everything is fine now. Present in array. Vertices are A, B, C, D. That is also okay. Can you help me now? Initial values. 0, null, infinite, null, infinite, null. All vertices information I took, I kept in the array. Every vertex information I took, I kept in the array. Please be careful. Present in array, I kept in array. Fine, that is also okay. And one more thing I want to ask you. A vertex will be relaxed. A vertex will be relaxed in the case of the Bellman-Ford algorithm. How many times? A vertex will be relaxed in the case of Bellman-Ford algorithm. How many times? V minus 1 time. V minus 1 time. A vertex will be relaxed, right? V minus 1 time in the Bellman-Ford, but in the case of the Dijkstra's algorithm, 1 time. Please be careful. V minus 1 time. Where V is number of vertices. Can you help me now? How many vertices in this graph? 4. So, Bellman-Ford algorithm, a vertex will be relaxed how many times? V minus 1. How many times? 3 times. Let me write now. I is equal to 1 first time. I is equal to 2 second time. I is equal to 3 third time. Right? I is equal to 1, I is equal to 2, I is equal to, because the 4 vertices. Right? 3 times a vertex will be relaxed. See, I is equal to 1. First time I will do relaxation. Second time, third time, V minus 1 times I can do. So, 3 times. Now see the interesting answer. See the interesting answer. Listen everyone. This is very, very crucial point. If you don't listen, you may lose this story. See this one. See correctly. How many people will give answer to me? How many people will give answer? See this diagram and talk. Vertex A relaxed, what is the meaning? Vertex A relaxed, what is the meaning? Vertex A relaxed means, right, adjacent people are 2 people, 2 places do decrease key operation. 2 places do decrease key operation. I think 1 decrease key is log V, 2 decrease keys, what is the answer? 2 log V here. If you want to, normally time complex, 2 log V. A adjacent people are 2 people, those 2 places do decrease key operation, 1 decrease key log V, 2 decrease key 2 log V. Similar way, what is the answer? B adjacent is going to be 2 people, those 2 places do decrease key operation, what is the answer? 2 log V. In the similar way D, so 0 log V. In the similar way C, what is the answer? I think 2 people, whether you do or not, it's okay. What is the answer? 2 people, isn't that 2 people you done? 2 log V, something like that. Can you help me one small line? What is this one? What is this one? Right? A relaxation time. This is B relaxation time. This one, D relaxation time, this one, right? C relaxation time. I think if you add all of them, what is the answer? These all, if you add, you know time complexity very well. If you add all, E log V, it is going to be E log V. Indirectly, directly what I want to say, listen, indirectly, directly what I want to say, if A relaxed, what is the meaning? Their edges are covered. A edges are 2. A adjacent people are 2 people, they covered. If B relaxed, their adjacent are covered. If C relaxed, their adjacent is covered. If you cover all the adjacent people, what is the answer? E edges are covered. Try to remember, in Dijkstra's algorithm, every vertex will be relaxed once. When you say all vertices relaxation one time is over, indication that E edges you covered. A will cover A edges, B will cover B edges, C will cover C edges. When you say all vertices relaxation one time over, what is the meaning? All edges are covered. So that is the reason E log V. See this one, A is relaxed, means A edges are covered, decrease key operation 2 times. B relaxation is over, B edges are covered, 2 log V. So decrease key operation, right, at the A adjacent people, decrease key operation at the B adjacent people. If you add all of them, right, what is the answer? All vertices are relaxed once is nothing but all edges decrease key operation one time you done. Please be careful. In the case of Dijkstra's algorithm, every vertex will be relaxed only once. But when you say a vertex is relaxed, what is the meaning? Their edges are decrease key done. Similar way next also, their edges are decrease key done. But when you say all vertices are completed, means Dijkstra's algorithm completed. What is the meaning? At the E edges decrease key operation you done, E log V. You know very well, right? Same thing happening here. Don't worry. Same thing happening here. Listen everyone. Listen. So if I ask you to do Bell-Manford algorithm, what is the first step you will do? Minimum parent you write. Next one. Give edge numbers also whatever way you want. That is also okay. 6 edges are there, 6 numbers you give. Now see the answer. In the case of Bell-Manford algorithm, a vertex will be relaxed one time or V minus 1 time. V minus 1. 4 vertices, 3 rounds required. Initial values I kept. Everything is fine. Now can you read one by one? See the interesting answer. From now onwards, careful. See the interesting answer here. See this one in this graph, in this particular graph. Please go to the edge number 1. I am doing the first round. First round relaxation is going on. Please see this one. Round number 1 I am doing. See the answer. See the answer. Go to the edge number 1. Go to the edge number 1. Round number 1 is going on. Go edge number 1. Can you read the edge number 1? A to D. Edge number 1 I am doing A to D. See this one. Edge number 1 is going to be A to D. Edge number 1 is going to be B to D. That's okay. Can you help me now? If edge number 1 B to D, what is the B value already? Infinite. What is the infinite plus 7? Infinite only. Means less is not coming. So I done decrease key operation on this edge, but is not changing. Edge number 1 I am doing decrease key operation. What is the meaning? Already B value infinite. Infinite plus 7. Infinite only. Means no change there. So edge number 1 decrease key operation I done, but is not changing. It's okay. In the similar way, go to edge number 2. What is the edge number 2? This one. C to D. C value infinite. Infinite plus 9. Infinite only. No change. Edge number 2 decrease key operation also completed. Let's go to the edge number 3. What is the edge number 3? B to C. B value infinite. Infinite plus 60. Infinite. No change. Edge number 4. Let me go. C to B. Edge number 4, let me go, C to B. What is C value? Infinite. Infinite minus 45. For infinite add anything. For infinite subtract anything. Infinite only. So no change. So edge number 4, decrease key, edge number 4, I done the decrease key operation, no change. That is also okay. Edge number 4 decrease key operation also over, no change. Until now, no change. Let's go to the edge number 5. A to C. A value 0. 0 plus 50. 50. From where? A. So I think edge number 5 decrease key operation I done, it changed. It's okay. Next one, edge number 6, let me read. A to B, A value 0, 0 plus 10, 10. From where? A. Edge number 6 also decrease key operation I done. Do you believe or not? All edges I done decrease key operation. All edges I done decrease key operation. Now, interesting answer. Interesting answer. So all edges you done decrease key operation, which is equal to Dijkstra's algorithm one time over. When you say Dijkstra's algorithm is completed, what is the meaning? All edges are decrease key operation done. Dijkstra's algorithm one time over, all edges decrease key operation is done. Similar way, right? So all, see this one, all edges you done the decrease key operation means indication that at every vertex you done the relaxation now. See, in the case of the Dijkstra's algorithm, vertex by vertex you go, but here edge by edge you will go. But one thing, E will also cover all edges. E will also cover all edges. Edge number 1 decrease key operation, edge number 2 decrease key operation. All edges decrease key operation, one round over. What is the meaning? Dijkstra's algorithm one time completed. In Dijkstra's algorithm, vertex by vertex you go. Finally, all edges decrease key operation done. Here also, all edges decrease key operation you do, but you will go edge by edge. Okay, whatever changes you got, it's okay. All edges decrease key operation one time you done. Right? That's okay. Let me write the answer. So, round number 1 is over. This is the answer. So, when you say round number 1 is completed, what is the meaning? All vertices are relaxed once, which is nothing but all edges decrease key operation done. Please check. Here see, all vertices are relaxed once. All vertices are relaxed once means all edges decrease key operation is done. In the similar way here also. Round number 1 is over means all vertices are relaxation one time done, which is nothing but all edges decrease key operation I done. Simply, right, Dijkstra's algorithm will go vertex by vertex, but he will also cover all edges. He will go directly edge by edge. Right? So that both will be similar. Can you help now? Round number 1 over means how many edges are covered? E edges are covered. How many edges are covered? E edges are covered. And one more. E edges decrease key operation. Everyone is decrease key operation. E edge decrease key operation. Try to remember, if you do decrease key operation in the min heap log V, right? If you do decrease key operation in array, constant. Right? E edges you done the decrease key operation. Here also E edges you done the decrease key. Here also E edges you done the decrease key operation. But he will go vertex by vertex. But he will go edge by edge. But he will also cover all edges. Every edge decrease key operation in the min heap log V. But in the case of array, constant. Now, those people who are having small doubt also, let me do one more round also. Let me give clarity first. Why I went to the array, all the things I will explain. Right? Let's go to the round number 2. See the interesting answer. Round number 2 I am doing. Round number 2 means at listen everyone, all edges, again do decrease key operation. One time decrease key operation, all edges over. Let me do second time decrease key operation, all edges. Let's go to the edge number 1. That is the reason edge numbers I given. So that you will go some systematic order. Some order you have to follow. Just give whatever order you like in the first time. Just follow that order. Let's start now. Edge number 1. Edge number 1 decrease key operation. See the answer. B to D. B value 10. 10 plus 7. 17. Comparing infinite 17 better. From where? B. Edge number 1 decrease key operation over. Edge number 2. C to D. C value 50. 50 plus 9. 59. But 17 better. Don't change. Edge number 2 decrease key operation also over. Let's go to the edge number 3. B to C. B value 10. 10 plus 60. 70. But 50 better. No change. Edge number 3 decrease key operation over. Go to the edge number 4. C to B. C value 50. 50 minus 45. See 5. There is 5 from where? C. Edge number 4 also completed. Let's go to the edge number 5. A to C. A value 0. 0 plus 50. 50 better. Let me go to the edge number 6. A to B. A value 0. 0 plus 10. 5 better. So, all edges again decrease key operation I done. Which is nothing but all vertices relaxation one more time I done. Which is nothing but all edges decrease key operation one more round I done. Let me write now. 0 null. A. B. 5C. C, 50 A, D, 17 B. And one more thing, all edges should decrease key operation again. E edges I done decrease key operation, every decrease key operation run in the array, constant time. Now some students are asking one interesting answer. Sir, why are you going to the array? Why not min heap? Try to remember, if you always want to delete minimum, then min heap required. I don't want to delete minimum. If I delete, see this one. If I delete after doing the A, relaxation and all, if I delete, how can I do second round? If you always want to delete minimum, min heap required. In the case of the Dijkstra's algorithm, always minimum delete. Right? Here you don't delete. What is the reason? If you delete, how can you do second round? If you don't do second round, you cannot get the answer here. Because of negative there, many rounds you have to do. Because of only positive, one round enough. Dijkstra saying that all edges decrease key operation I will do one time, which is nothing but all vertices relaxation one time. I will do one time, I will get the correct answer. True for positive. For negative it is not. Many rounds you have to do. If you want to do many rounds, how can you delete every time minimum, minimum, minimum? If you delete always minimum, 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 second round how will you do? First round itself all out. How can you do in the second round? So you will go vertex by vertex, vertex relax, delete, vertex relax, delete, but he is not like that. Vertex by vertex, you don't go, edge by edge you will go, because he knows that same vertex should be done many times. The reason why I am not using min heap is, if I use min heap, always I have to delete minimum, minimum, minimum. Right? Here I don't delete minimum, 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 because I have to do many times. That is the only difference. So array, you only say it is not sorted array also, normal array. In the normal array, if I change something, no effect to other people. Right? Constant time enough. Right? Random array there, go to the 50th place, already 50 there, replace 50 by 20, no effect to other people, because it is a normal array. That is the reason. Let's do the one more round. Let's do the one more round. V minus 1 rounds required, last round is going on. Let's do same story. Go to the edge number 1. Edge number 1, right? B to D, B value 5, 5 plus 7, 12. From where? B. That is edge number 1. Edge number 2, C to D, C value 50, 50 plus 9, 59, 12 better. Edge number 3, B to C, B value 5, 5 plus 60, 65. Right? I think no change. Edge number 4, 50 minus 45, 5, 5 better, no change. Edge number 6, edge number 5, A to C, A value 0, 0 plus 50, 50 better. Edge number 6, A to B, A value 0, 0 plus 10, but 5 better. So these are the changes. Whatever changes are there, let me write here. Whatever changes are there, let me write here. So A value 0 null, B 5C, C 50A, D 12B, 12B, right, like that. All the modifications, whatever is there, I written. So E edges decrease key operation, everyone is constant, E into constant. See, no deletions, nothing there. If you delete, how will you go further? And one more. B vertices are there, V minus 1 rounds are enough. If anyone having small doubt also, let's do one more round for verification. I is equal to 4, only for verification. This is for verification. Right? Verification. If you want, I will write verification. This is for verification. This is for normal, right? Normally V minus 1 required. V minus 1 rounds for normal process. If you want, you can verify also. Verification purpose, one more round. If you want, you can check it, don't change. Let me try, if you want. Vth round not required, V minus 1 rounds enough. Only for verification I am doing. Let's do the last round, only for verification. So, edge number 1, B to D, B value 5, 5 plus 7, 12, already there. Edge number 2, 50 plus 9, 59, 12 better. Edge number 3, right? Edge number 3, 5 plus 60, 65, 50 better. Edge number 4, 50 minus 45, 5 already there. Edge number 5, right? 0 plus 50, 50 better. Edge number 6, 0 plus 10, 5 better. See, nothing changed. Right? Fine. Whatever you got, it's okay. Now see the answer. What is the Bellman-Ford algorithm time complex? How many rounds you done? V rounds. Including verification, V rounds. Every round time, E. So time complex of Bellman-Ford algorithm, V into E. Now few questions I am asking you. Why I am not using min heap? If you want to delete always minimum, then only go to min heap. Otherwise not required. And one more. How many rounds required? How many rounds of relaxation required? What is the answer? V minus 1 rounds enough. Every vertex will be relaxed. V minus 1 time, but Dijkstra's 1 time. But one thing, all vertices are relaxed 1 time means all edges decrease key operation done 1 time. So in the Dijkstra's algorithm, all vertices relaxation 1 time over, all edges decrease key operation 1 time done. You will go vertex by vertex, you will go edge by edge. 1 round, all edges are decrease key. Because of array, decrease key operation constant. There, right? Because of min heap log V. See, if you want, you can check nowhere log came here because no min heap. There many times log came because of min heap, right? Next one, here nowhere I am deleting minimum because it is not min heap. If I delete, how can I go further, right? This is the story. Can you help me now? If I give from next time onwards, see this one. Next time onwards, if I give any problem, if I ask you apply Bellman-Ford, what is the answer? As soon as you take the graph Bellman-Ford, right? Simply infinite null, like that, keep everywhere. First one 0 null, source, remaining all are infinite null. That is the first step. Afterward, edge numbers you give. Whatever order you want, you can give. Afterwards, round number 1, round number 2 and so on. V minus 1 rounds you do. Right? In the last round, answer will not change. If you want, you can check. So V rounds, every round is E time, total time complexity VE, because nowhere log came because of it is not mini heap. Next one, interesting answer I want to say to you, interesting answer. Can you help, finally, A to A, what is the minimum cost? 0. Finally, A to B, source is A to B, finally minimum cost 5. A to C, final cost 50. A to D, final cost 12. If you want, you can check. 0, 5, 50, 12. Manual checking already there. See this one, 0, 5, 50, 12. See, exact answers came. See this one, Dijkstra's algorithm may fail for a few people, but Bell-Manford algorithm, even though negative there, it will always give correct answer. Please check. It is given correct answer. Please verify. Now, it is the correct time to ask, is Bell-Manford is working for only positive? Yes, it will work. The only thing is the time complexity more. You are doing many rounds, of course time complexity will increase. Can you help in only positive? Better idea. Go to Dijkstra's. One negative also there. So Dijkstra saying that I may give correct answer, I may not give correct answer. When you have dilemma, then go to Bell-Manford algorithm. It will give positive also, for negative also, for both also it will work. Negative one also you see, come to Bell-Manford. All positive, go to Dijkstra's. Most practically used algorithm, Dijkstra's algorithm. Right? No requirement of doing manual checking. Without manual checking also I said to you how to do. Only for your convenience I explained all three. Listen everyone now, Bell-Manford means do this only. Dijkstra's means do this only. Right? For your convenience I explained everything. Right? Because of new thing is coming, I don't want to confuse you. First I done manually how it look like. Is it Dijkstra is giving that one? No. Next one is Bell-Manford is giving? Yes. Can you help me from this? What is the conclusion? Graph contain positive edge weights, right, or negative edge weights. Bell-Manford algorithm will always give correct answer. Positive edge weights or negative edge weight, or means what? Any one or both. Then it will always give correct answer. Right? Dijkstra's algorithm only positive you will give correct answer. Negative Dijkstra's algorithm may fail. Right? Please be careful. See this one. One more example. Right? Take this problem. A, it is 5. It is not 23, please be careful, it is minus 23, please be careful. A, right, 10, sorry, A to B is 10, B to C is 20, C to B is minus 23, C to D is 5. This is the given graph. Now what will you do is, right, there is something new, that is the reason I don't want to confuse you, I am doing manual checking. In exam not required. One new point is there to explain that clearly, I am doing manual checking. Manual checking I am doing. A to A how much? A to B how much? A to C and A to D. So on this particular graph, manual checking I am doing. Right? After manual checking, so what is our goal? From source to every other vertex, what will be the shortest path? That is the goal. Manual checking I will do. Right? Because something new coming, that is the only reason. Afterwards, you know very well, right? Dijkstra's algorithm, because of negative, Dijkstra's may fail. Only for namesake, I will do Dijkstra's. Only for namesake. Dijkstra's may fail, right? Everyone know. Graph contain negative, Dijkstra's may fail, but our actual goal is Bell-Manford I will do here. This is our actual goal. Right? Bell-Manford. Within few minutes I will do. Let me complete formalities. Right? Manual checking. Let's start. What is the first step? Manual checking. See the answer. See, make sure that everyone listen. One interesting thing is there. That is the reason I give in this problem. See this one. As usual, 0 null, infinite null, infinite null, infinite null. See, manual checking, no logic, nothing here. Manual checking. Can you help me now? A to A, 0. That's okay. A to A is 0. I am okay with that. Can you help me now? What is the A to B? A to A is 0. I am absolutely okay. What is the A to B? Let me check here. A to B, 0 plus 10. What is the answer? 10. From where? A. A to A is 0, I am okay with that. What is the A to B? 0 plus 10, 10. Right? From where? A. That is also okay. But one thing I want to ask you, see this one. One thing I want to ask you, this is 10 from A, I am okay with that. Can you help me now? What about B to C? See the answer. See this one, A to B is already 10, that's okay. Next one, what about A to C? See, already B is 10, 10 plus 20. What is the answer? 30. Right? 30 from where? B. So, A to C I want, right? Already B value 10, 10 plus 20 is 30, 30 from B. That is also okay, right? Until now fine. But see the interesting thing. See this one? See the interesting thing? A to B, if you observe 10 there, right? A to B, if you observe 10 there, but see this one, A to B 10, if you go like this and if you come back, what is the answer? You only say 30 minus 23, what is the answer? 30 minus 23, what is the answer? I think 7. I think because of change, when I come back, right, little bit less coming, so I will take. From where you came, see. If I go A to B directly, 10, right, after making one round, if I come back, I think what is the answer? 10 plus 20, 30, 30 minus 23 because of negative, 30 minus 23 which is going to be 7. Normally if you come back, cost will increase, but cost decreasing because of negative. So I think it is 7. Some people are asking, sir, if E changes, E will also change. Can you help me? What is 7 plus 20? 27, comparing 30, 27 is better. 27, from where? B. I think because of E change, E will also change. What is the answer? 27 minus 23. What is the answer? 27 minus 23. What is the answer? I think 4. From where? C. Because of E changes, E will also change. So what is the answer? 4 plus 20. What is the answer? 24. From where? B. I think this is keep on changing. Please check. That is the reason I given this problem. That is the reason. Can you help you now? What is the first time? 10. Next to 7. Next to 4. If you observe, 3 difference. 3 difference. I think 10 minus 3, 7. 7 minus 3, 4. 4 minus 3, 1. 1 minus 3, minus 2. It will keep on going. Can you help me now? Because of it changes, C will also change. What is the first time? 20. Next one, after first time is going to be what is the answer? 30. Next time, 27. Next time, 3 remove, 24. 3 remove, 21. It will also continue like this one. It will also continue. Can you help me? How many times? Because of every time changing. Every time I will rotate. There is a cycle. In that cycle, every time changing going on. Every time I will rotate. Can you say how many times I will rotate? Rotate infinite time. It will become minus infinite. What is the meaning of minus infinite? Very small value. Decreasing. If you do infinite time, it will become minus infinite. Try to remember, in all the infinites, in all the values, big value is positive infinite. Right? Small value is negative infinite. It is very small value. Some people are asking, sir, why you stopped? Very small value came. How many times you repeated? Infinite time. Infinite times you repeated. Value increasing or decreasing? Decreasing. Infinite times going on. Every time decreasing. So it became very small value minus infinite. Right? And one more thing. Can you help me now? First time. What is the first time? 30. 30 plus 5. This became 35. From where? C. Second time. 27 plus 5. What is the answer? 32. From, right? C. Next one. One more time. What is the answer? 24 plus 5. 29. Right? I think C. I think it is also decreasing. 3. I think E will also becomes, right, minus infinite. What is the first time? 35. Next time? 32. Next time? 29. Continue. Minus infinite. Right? Like that. And one more. One small line. Let me write. One small line. See the answer. See everyone now. See this line only. Carefully. In this particular one, if you observe, is there any cycle? Yes, cycle is there. In this cycle, what is the total sum? Minus 3. This is called as this one. There is a cycle. In that cycle, total sum of the edge weights is negative. This is called negative edge weight cycle. Negative edge weight cycle. In the given cycle, total sum is negative. That is called negative edge weight cycle. I am not saying negative edge weight. Negative edge weight cycle means in the given cycle, total sum of edge weights is negative. That is called negative edge weight cycle. If negative edge weight cycle is there, what is the meaning? Because of cycle and one more. Because of negative value decreasing. So always will decrease. I want less, so it is always decreasing also. I will continue infinite time. Finally, I got minus infinite. So see this one. There is a negative edge weight cycle. Those people who are participants in the negative edge weight cycle, to go from source to that vertex, guarantee minus infinite. Because they are always changing. They are always decreasing. From source to them, if you want to go, because of they are always decreasing, their value becomes minus infinite. But one thing is, listen, this person not part of the negative edge weight cycle, but he is depending upon negative edge weight cycle. Because of he is depending, they changes means he will also change. They changes means he will also change. He will also become minus infinite. He will also becomes minus infinite. The purpose of this problem, can you help me now? What is the purpose of previous problem? Introducing negative edge weight. Here, introducing negative edge weight cycle, right? That is the only purpose. Don't confuse. Whenever new things will come, instead of confusing, Please get that point. If you are not getting, listen again. Concentrate properly. The purpose of this problem, introducing negative edge weight cycle. What is the meaning of negative edge weight cycle? In the given cycle, total sum of edge weights is negative, that is called negative edge weight cycle. What is the problem with the negative edge weight cycle? Because of they are negative means decreasing, cycle and decreasing. I want less. Every time cycle means what? Every time you can repeat, every time less coming, I done almost like infinite time, it became minus infinite. Now it is the correct time to ask you, to this problem, A to A, what is the minimum cost? 0. A to B, minimum cost minus infinite. A to C, minimum cost minus infinite. A to D, minimum cost minus infinite. And one more, who got the minus infinite? Those people who are part of the negative edge weight cycle, they got minus infinite. Those people who are depending upon negative edge weight cycle, they also got minus infinite. If you want, you can check. A is neither part of the negative edge weight cycle, not depending. See this one. Afterwards, maybe you will go to negative, but see this one. Until now, no negative. So he is not depending, he is not part of the cycle. He is not part of the negative edge weight cycle, he is not depending also. That is the reason you don't have any negative. But this person, not part of the negative edge weight cycle, depending. What is the meaning? After this, he will come. He changes, he will also change. That is the meaning of depending. But when you say part of the cycle, they are the participants in the cycle. So, listen everyone, to this problem, actual answers are these. But Dijkstra's, do you believe on a Dijkstra? See this one. To get this as minus infinite, to get this as minus infinite, to get this as minus infinite, you have to do infinite times. But Dijkstra's will do one time only. Guarantee will give wrong answer. Negative edge weight cycle is there. Guarantee Dijkstra's will give wrong answer. What is the reason? He is not at all bothered. Negative also. Why you bother about negative edge weight cycle? To do negative edge weight cycle correctly, right? Infinite times you have to repeat. But Dijkstra's will repeat one time only. So forget about Dijkstra's will give right answer, wrong answer. Only for namesake we will do Dijkstra's once. Only for namesake. See this one? Very simple. Dijkstra's algorithm everyone know also, only for namesake I am doing. A, B, C, D, 0 null, infinite null, something like that. Right? If you want, I will change the values. Right? So I am doing Dijkstra's. Only for namesake I am doing Dijkstra's. 0 null, infinite null, infinite null, infinite null. See this one. Without manual checking also, for which vertices Dijkstra's will give wrong answer, you know very well that procedure. Right? One way is do manual checking, afterwards you verify. One more way, without manual checking also, directly you can give to which Dijkstra's will give wrong answer. If you want, one more time I will explain. Without manual checking, how to say Dijkstra's is giving wrong answer to whom? Right? I will explain. So what is the answer? I think everything is there. Now delete. A deleted. Forget about the manual checking. To which vertices Dijkstra's will give wrong answer? For this problem, let me check. Delete. A deleted. A deleted. Can you help me now? A adjacent people. Who are those? Only B. So what is the answer? 0 plus 10. What is the answer? 10 from A. Right? So I think B. 10 from A. Infinite null, like that. Next one. If you delete now, B came out. B's came out. Now see the answer. If you delete now, B's came out. Can you say who are the B adjacent? Only C. B adjacent is only C. Please check. Right. Can you help me now? B adjacent is only C, is not over also. Right? 10 plus 20. What is the answer? 30. From where? B. 30. From where? B. This is infinite null. That's okay. Now I think now here problem going to be happen. Please take care. Right? B. That's okay. Now see if I delete now, who came out? C. Can you help me now? Why C is came late? What is the reason? C is big value. That is the reason he came late. Who came first? A. Because A value 0. That is the reason he came out. Afterwards B came out. What is the reason? B value is next one 10. I think this is next better. First better is A 0. Next better is B 10. That is the reason they came. Now who came late? C. C is came late. Now can you help me now? Listen correctly this line. Can you help me now? Who are the C adjacent? Forget about they are over or not over. Who are the C adjacent? C adjacent D also and B also. Can you help me now? C adjacent is B also, D also, that is fine. Right? At which place I have to do decrease key operation? According to Dijkstra's. C adjacent is B also, D also. That is okay. According to Dijkstra's, to which vertices I have to do decrease key operation? Dijkstra's simply saying that, right? So C adjacent is B and D, but he is already over. He is already over. He is the best person. That is the reason before C, B done. Dijkstra saying that he is already done. He is already done. Please don't do decrease key operation to him because he is already better. He is done. But one thing, right? Negative is there. Dijkstra saying that don't do decrease key operation, but negative there. I have doubt on Dijkstra's. Right? So only for namesake verification purpose I am going. I don't change verification. Dijkstra saying don't go. Negative is there. I have doubt on the Dijkstra's. I am going and verifying. Let me verify. 30 minus 23. What is the answer? 7. Okay, it's the 10. 7. I want to change. I cannot change. What is the meaning? Dijkstra's fail here. Dijkstra saying don't go. Because of negative I have doubt. I went and verified. Yes, there is a wrong here. There is a wrong. So I don't change, but I got to know there is a wrong here. No requirement of manual checking. Go and verify. Yes, wrong is there. So this is wrong. But one thing, this is wrong means based on wrong person, he is also wrong. Because of he is wrong, based on wrong person, he is also wrong. 3 people will give wrong answer. Please be careful. Like that you have to. There is no requirement of doing this. Dijkstra say don't go. Because of negative, you have doubt on Dijkstra's. You go and verify, but don't change. So it is wrong. Wrong plus something also wrong. Wrong plus something also wrong. Please take care. So 3 people wrong. If you want, you can verify. Now can I help you now? C deleted. Who is the C adjacent according to Dijkstra's? C adjacent according to Dijkstra's. What is the answer? B and D. C adjacent is B and D, but B is already over. Only D according to Dijkstra's. Go and verify. So what is the answer? C adjacent according to Dijkstra's, D only. What is the C value? 30. 30 plus 5, 35. From where? C. I think now C also deleted. What is this value? 35C. Now let me delete. D also deleted. No one is there. Stop it. D also deleted. No one is there. Stop it. Now I am stopping now. I am stopping. After stopping, please verify. Who is wrong answer? A 0 according to Dijkstra's. Manual also 0. B according to Dijkstra's 10. Actual answer is minus infinite series. So it is wrong. B wrong. Next one. C is according to Dijkstra's 30, but actual answer is minus infinite. It is also wrong. Next one. Manual checking not wrong, right? Dijkstra's is wrong, you know. Next one. D, 35 is coming according to Dijkstra's. Actual answer is minus infinite. So for this problem, if you apply Dijkstra's, 3 OTCs, wrong answer will come. Except A, all people are wrong. How will you check? Whatever I said to you, like that you follow. This also you can do, but lot of time will waste. Right? Fine. Okay, fine. Purpose of this one, checking negative edge weight cycle and all. That is the only reason I explained this. Right? Okay, whatever you got, it's okay. Let's come to the actual problem. That problem, if you do Bell-Manford, right, how to solve, I will explain. See this one, I will explain. See correctly? See correctly this one, A. So on this graph, if you apply Bell-Manford, what will be the answer? Right? I will do now. Listen everyone now. Almost we are closing of the Bell-Manford. See this. A, B, C, D. Present in array. Present in array initially 0 null, infinite null. See this is the way how the Bell-Manford will be done. Present in array you write. For every person is infinite null, only for source 0 null, that is okay. Can you say how many vertices? 4. How many rounds required? 3 rounds. 1, 2, 3. 3 rounds. Right? Verification purpose, 1 more round. Normally in the verification nothing will change. This is for verification. Right? Normally is V minus 1, totally V rounds. This is for verification. Right. So I am doing 1 by 1 now. V rounds, right? Actually V minus 1 including verification round, V rounds. So I am starting. Can you help me now? Bell-Manford algorithm first step. After everything is ready, can you say Bell-Manford algorithm first step? What is the answer? Give edge numbers whatever order you like. Edge number 1, edge number 2, whatever order you like, no objection at all. Give edge numbers. Yes, I given. So Dijkstra's will go vertex by vertex. Bell-Manford will go edge by edge. But at the end of the day, right, how many edges he will do decrease key, he will also do same. But Bell-Manford will do many rounds, he will do 1 round. Right? So I think edge numbers given, start now. Decrease key operation at every edge. Start for the first edge, C to D. Let me give those also. What is the answer? 0 null. It is the infinite null. It is also infinite null. It is also infinite null. Now see this one. Edge number 1, C to D. Edge number 2, B to C. edge number 3, C to B, edge number 4, A to B, like that all edges are there, right? So I am starting the decrease key operation at every edge. Can you help in the first edge, C to B, all edges are over, then change it, right? I am starting, edge number 1, C to D, edge number 1 is C to D. Can you help in what is the C value? Infinite plus 5, right? So I think C to D, C value, infinite plus 5, infinite, no change, edge number 1, no change, edge number 2, B to C, B value, infinite plus 20, infinite, no change, edge number 3, infinite minus 23, infinite, no change, edge number 4, 0 plus 10, 10, from where? A, change is there, somewhere change there, right? Now definitely if at all no change there, stop, right? So if you see all the people do one time, no change there, you can stop. Let's see here, what is the answer? You say what is the answer? Whatever, all edges decrease key operation one time over. Let me write the answers. 0 null, B, 10 A, C, infinite null, D, infinite null, right, like that. So all edges, what is the answer? E. Right, one round over. Let's go to the one more round. Actually 3 rounds required. Verification purpose one more, totally 4 rounds. One round over. Let me go to the remaining 2 plus 1 also. Let's go to the second round. Same story. What is the answer? Edge number 1, C to D, C, infinite. So no change. Edge number 2, see the edge number 2, B to C, B value 10, 10 plus 20, 30. From where? B. Edge number 2 also over. Edge number 3, C to B, C value 30, 30 minus 23, what is the answer? 7, from where? C. Edge number 3 over, edge number 4, 0 plus 10, 10, but 7 better, no change. All edges decrease key operation one time over, let me write the answer. A, 0 null, B, 7C, C, 30B, D, infinite null. So E. Right? I think this is also completed. Let me go to the next one now. Third round. V minus 1 rounds. I think last round. Verification, it's okay. Last round. Let's see. Go to the next one. Edge number 1, C to D. C, 30. 30 plus 5, 35. From where? C. Edge number 1 over. Edge number 2, B to C. B value 7. 7 plus 20. What is the answer? 27. From where? B. Edge number 3, 27 minus 23. What is the answer? 4. From where? C. Next one, edge number 4, 0 plus 10, 10, but 4 better, right? This is, let me write the answer, 0 null, this is 4C, this is 27B, this one, 35C, right, like that. So this is also E time, fine. So V minus 1 rounds over, verification round value cannot change, right? Let me do only for namesake, value will not change, still I will do, right? Let me go to the round, right, edge number 1, 27 plus 5, 32. From where? C. Edge number 2. 4 plus 20, 24. From where? B. Edge number 3. 24 minus 23, 1. From where? C. Right? Edge number 4. 0 plus 10, 10, but 1 better. Let me write. 0 null. This is, what is the answer? What is this value? B. 1C. This one? 24B, this one 32C, right? This is E. Fine. So I am thinking that everything is fine now. Can you help? Verification round it cannot change, but some people are changing. Can you say who are changing? Verification round no one can change, but some people are changing. Who are changing? I think see 4 1 E changing, 27 24 E changing, 35 32 E changing. I think these 3 people are changing. Indication that verification round also, if anyone changing, indication that they are part of the negative edge weight cycle or depending upon negative edge weight cycle. That means, what is the meaning? They will change every time. Negative edge weight cycle means what? They will change every time. In the V round also someone changing means they are part of the negative edge weight cycle or depending upon negative edge weight cycle, means they will change every time. So no need to continue further. All those 3 values you can make it as minus infinite. They will change every time. So I think now people got to know what is the purpose of the last round. What you are verifying, negative edge weight cycle is there or not. In the previous problem, last round no change. What is the reason? Negative edge weight cycle not there. Now in this problem, last round also changing. What is the meaning? Negative edge weight cycle is there. In the previous problem you check. Negative edge weight cycle not there, last round no change. Here changes are there, negative edge weight cycle is there. That is the purpose of this. right? I think last round whoever changing, they are part of the negative edge weight cycle or depending. Their answers are going to be minus infinite. Can you help me now? Can you help me now? Right? What is the shortest path from A to B? If I ask, someone mentioned that minus infinite. What is the meaning? Indication that the shortest path from A to B is minus infinite. What is the meaning? Minus infinite is a very small number, but one thing, infinite means undefined. Try to remember, right? To go from A to B, cost is minus infinite means negative edge weight cycle and all. Indirect way of saying is going to be because of minus infinite, undefined. Undefined, right? I want some answer. You are saying minus infinite, right? So try to remember, if the graph contain negative edge weight cycle, right? For some people you will give correct answer. To whom you are given correct answer? I think see, A to A 0, right? So those people who are part of the negative edge weight cycle, those people who are depending upon negative edge weight cycle, right? Answer is undefined. See, minus infinite means undefined. Actual answer is minus infinite only, that is fine, but because of infinite it is undefined. Because of infinite it is undefined. I am asking what is your value, you are saying minus infinite, means undefined. Because of negative edge weight cycle it is happened. Okay, whatever you got, it's fine. I am thinking you are okay now. Now it is the correct time to ask you, please listen, please listen. When the Bellman-Ford algorithm will give correct answer, what is the answer? Only positive, right? Only positive or a combination of positive negative, it will give correct answer. If the graph contain negative edge weight cycle, Bellman-Ford algorithm will give for some OTCs correct answer like A, right? For some OTCs, right, it cannot give correct answer because result is undefined because of negative edge weight cycle depending or part of it. Right? These people, right? Bellman-Ford algorithm not able to give correct answer because result is undefined. The reason why it happened is they are part of the negative edge weight cycle or depending upon negative edge cycle. See, nothing wrong happened. Bellman-Ford algorithm done the things which is possible, but unfortunately minus infinite came which is undefined. Because of undefined, right, it is not giving correct answer. Undefined means it is not giving correct answer. For some OTCs correct answer, see, A to A is 0. Supposing that there are some more OTCs where they are not part of the cycle, not depending on cycle, definitely Bellman-Ford algorithm will give correct answer. But those people who are part of the negative edge weight cycle, depending upon negative edge weight cycle, right, answer is going to be minus infinite, which is undefined. Suppose the negative edge weight cycle not there, only negative edge weight is there, it will always give correct answer. Okay, what is the time complexity? V times E, so order of VE. Time complexity order of VE, and one more, you are using array data structure, that there is a no logs k. Last round for verification, in the last round also someone changes, indication that negative edge weight cycle is there. Right, those people who are changes, they are part of the cycle or depending upon cycle, to them, right, shortest path is not able to find out, means answer is undefined. Negative edge weight cycle not there, right, answer is defined for everyone. Okay, I am thinking that you are little bit okay, right? Can you help first step of Bellman-Ford algorithm? Just write every way, right? 0 null for the source, remaining infinite null like that. Next one, give edge numbers, whatever order you want. Next one, right? Round number 1. For all edges do decrease key operation one time. After doing all, then write the value. Don't write in the middle. Just to do round number 1 properly, then write. Round number 2 also do properly, then write. Just do like that V minus 1. Next one, last round do only to verify cycle there or not. If cycle there, who are part of the cycle, to them answer is not defined. For other people answer is defined. By seeing the V round, I can say cycle is there or not there. No change in the, see this one. V minus 1 round and the V round, some change there. So cycle is there. Whoever changes, they are part of the cycle. Their answer is undefined. Supposition that V minus 1 round, V round same, cycle is not there. Means Bellman-Ford algorithm will give for all the people correct answer. Cycle is there. For some people, it is not able to give correct answer because answer is undefined. So let me write only for namesake all these points, right? See the first point. If graph contain, you know all these points, only for namesake I am writing. If graph contain, right? I am reading. Roughly I written, I am reading now. Roughly I am written. See this. First point. Roughly I written, I am reading also. Please see if anything not clear. If graph contain all positive edge weights, then Dijkstra's algorithm always correct. Otherwise, it may fail. What is the meaning? One negative also, it may fail. Second point, if graph contain positive or negative edge weights but not negative edge weight cycle, then Bell-Manifold algorithm will always correct. 3. If graph contain negative edge weight cycle, then Bell-Manifold may give wrong answer for few vertices which are part or depend on negative edge weight cycle, because answer is undefined to them. But for others, means those people who are not part of the cycle, who are not depending, means that is the meaning of this. For others, it will give correct answer. It will give correct answer. And one more, how Bell-Manifold will identify graph contain negative edge weight cycle or not? In the Vth round also, some changes there, right? So Bell-Manifold algorithm got to know negative edge weight cycle is there. Supposition that is this one. Supposition that sometimes what happened is graph contain negative edge weight cycle, right? But still Bell-Manifold algorithm not able to find it. What is the reason? The reason is from the source it is not reachable. In the given graph, there is a one negative edge weight cycle, right? It is not reachable from source. If it is not reachable, no one can do that. Bell-Manifold algorithm will find out all negative edge weight cycle present in the given graph if they are reachable from source. If they are not reachable from source, I am not able to reach it. Even though there, how can I see? Right? Let me write that also. 4. Bell-Manifold will find all negative edge weight cycles present in given graph. Bell-Manifold will find all negative edge weight cycle present in the given graph if they are reachable from source. Otherwise not possible. Bell-Manifold will find all negative edge weight cycles present in the given graph if they are reachable from source. Right? Please be careful. From this, what are the final suggestions? Final suggestion, only positive, go to Dijkstra's. One negative also, then go to Bell-Manifold. Negative edge weight cycle is there. Bell-Manifold also may say for some people, not for some people, right? I cannot give because result is undefined. Actually, it is giving because of minus infinite is undefined. When you say you are giving, some number should be given. If you say minus infinite, there is no meaning in that. That is the reason he is saying I am unable to give proper answer if the graph contain negative edge cycle who are part of it. For them, correct answer I am unable to give. That is what you want to say that. Okay, fine. This is the story. Please be careful. Totally 4 problems. Read all of them. Right? So next topic in greedy chapter, which is very, very important one, is going to be minimum cost spanning tree. Right? So I written on the board also, see, minimum cost spanning tree. In this minimum cost spanning tree, major one, right? Spanning tree. I written the definition also. Within few minutes I will explain. Let me read the definition. A subgraph S of the given graph G is said to be spanning tree if and only if. First point, S should contain all vertices of G. 2. S should contain V minus 1 edges only, where V is number of vertices. 3. S cannot contain cycle. Right? This is the definition. Right? Please be careful. Minimum cost spanning tree is very, very important. So I started. Fundamental thing which is required is going to be spanning tree. I written the definition also. A subgraph S of the given graph G is said to be spanning tree if and only if 1. S should contain all vertices of G. 2. S should contain V minus 1 edges where V is number of vertices. 3. S cannot contain cycle. Right? This is the definition. With the help of one example, everything clear. See the example. Now. A, B, C, D. See this one, it is the graph. To this graph, I am drawing possible spanning trees. Please be careful. To this graph, possible spanning trees I am writing. Can you help me now? This given graph is G. Given graph G, I am taking one subgraph S. Given graph G, I am taking one subgraph S. See the first property. What is the first property? S should contain all vertices of G. Yes. That is the first point. S should contain all vertices of G. Yes, I took. Next one. Next one. If the G contains this one, if the G contain 4 vertices, S also contain 4. That is okay. Next one. Next one. Can you help me? How many vertices are there? 4. If the graph contain 4 vertices, spanning tree also contain 4 vertices, I am accepted. And one more thing is going to be, if the graph contain 4 vertices, spanning tree should contain 4 minus 1. How many? 3. 3 edges only it should have. It may be having more edges. Graph may be having more. Can you say graph contain maximum how many? V into V minus 1 by 2 edges are there. But spanning tree contain V minus 1 edges only. Not more, not less. See this one. S is a subgraph of the given graph G. Then I can say S is a spanning tree. First one. S should contain all vertices of G. But S should contain V minus 1 edges only. V minus 1 edges only. Can you help me now? Yes, I think V value here 4. 4 minus 1 is going to be 3. Here 3 edges only should be there. Let me write the 3 edges. 1, 2, 3. 3 edges. But what is the third rule saying? S cannot contain cycle. Please be careful. V minus 1 edges, okay. But with those V minus 1 edges, right? S cannot contain cycle. So I think cycle cannot be there. Cycle cannot be. So what should I do now? I think this one maybe. All vertices are there and V minus 1 edges are there and no cycle also. This is called spanning tree. This is called spanning tree. And one more thing, is it connected graph or disconnected graph? Right? It is a connected graph. What is the meaning of connected graph? In the given graph, between every 2 vertices, there is a path. Then I can say it is a connected graph. If you want, you can check it is a connected graph. See this one? Some people are asking, sir, how can you say connected graph? So between C to D, there is no edge. Edge may not be there, but a path there. In the given graph, between every 2 people, there is a path. Path means what? Collection of edges. Between every 2 people, there is a path. Then I can say it is a spanning tree. See this one? I think C to D, there is a path. Some people ask, what about A to D? There is a path like this. What about C to B? There is a path like this one. So spanning tree is a connected graph. Please be careful. How many people will go? If anyone asks you, spanning tree is a connected graph or not, what will you say? Spanning tree is a connected graph with minimum edges. Please be careful. A minimal connected graph is known as spanning tree. This is also a connected graph, but many edges are there. Please check. Spanning tree is a connected graph with minimum number of edges. If anyone asks what is the meaning of spanning tree, what will you say? Connecting all vertices with minimum number of edges is known as spanning tree. But when you say connecting all vertices with minimum number of edges, try to remember V minus 1 edges are enough. Some people are asking, sir, I have V vertices, I took V minus 1 edges, still graph not connected. To connect V people, V minus 1 edges are more than enough. After connecting with V minus 1 people also, still graph is not connected. What is the meaning? I think somewhere cycle is happened. When you say cycle, what is the meaning? Cycle is nothing but you are wasting some edges. Cycle is nothing but coming to the same point which already visited. What is the meaning? Some redundant work is going on. When you do redundant work with minimum number of edges, you cannot make it as connected. When you say minimum edges only I have, I want to make it as connected, means one also you cannot waste. What is the meaning of wasting? Cycle means wasting only. Now last time I want to ask you, what is the actual definition for spanning tree? I said to you, a subgraph S of the given graph G is said to be spanning tree. First rule, all vertices. Try to remember, spanning tree means covering all vertices. So take all. Next one, covering all vertices with minimum number of edges. I think to cover 4, 3 people are enough, right? 3 people I written. But while writing, please be careful. Cycle cannot be there. 4 people to connect 3 is more than enough. After adding 3 also, still not connected means somewhere cycle is happened. Please be careful. Again I am asking you, if anyone asks you what is the meaning of spanning tree, what will you say? Covering all vertices with minimum number of edges is known as spanning tree. When you say minimum, cycle cannot happen. When you say minimum, V minus 1 edges are enough. After adding V minus 1 edges, right, for the V vertices, still graph not connected, means somewhere cycle happened. means you wasted some edges. That is the reason it is not connected. Please be careful. Without wasting any edge, if you keep V minus 1 edges in V vertex graph, right, then it is called as spanning tree. Without wasting any edge. What is the meaning? Without creating cycle. V minus 1 edges keeping, right, with V vertices is known as spanning tree. This is the definition also. Please be careful. Right, so topic name is minimum cost spanning tree. For that major one required is spanning tree. I given the definition. This is the example for that. Systematic way of saying a subgraph S of the given graph G is said to be spanning tree if and only if S should contain all vertices, S contain V minus 1 edges where V is number of vertices, S cannot contain cycle. That is one way of saying. One more way. Covering all vertices with minimum number of edges is known as spanning tree. But when you say minimum, cycle cannot happen. So without cycle, V minus 1 people can definitely cover all vertices. Right? Fine. One spanning tree I written. Let me write one more spanning tree. To this graph, let me write one spanning tree I written. Let me write one more spanning tree. See the one more spanning tree. All vertices should be there. Yes. All vertices should be there. Yes, I written all. Next one. 4 vertices are there. 4 minus 1. 3 edges should be there without cycle. 3 edges without cycle. Let me write now. Check. So, I think see. 4 vertices, 3 edges, no cycle is there. Means connected only. See this one. 4 vertices and 3 edges you kept and no cycle also means you are not wasted any edge also. If you want, you can check it the connected graph. To cover 4 people, 3 edges are more than enough. After covering 4 with 3 people, still not graph connected means somewhere cycle happened. See, no cycle also. It is going to be a connected graph. Some people are asking, sir, how it is connected? How to go C to D? Like this you can go. How to go B to C? Like this you can go. How to go B to D? Like that it is. So, this is also a spanning tree. Some people are asking, sir, can you draw one more spanning tree? Can you draw one more spanning tree? Let me write now. See this one, interesting answer. A, B, C, D. This is very, very important one. Please see. A, B, C, D. Graph contain 4 vertices. Spanning tree also 4. That's okay. Graph contain 4 vertices. Spanning tree should contain V minus 1. What do you mean? 3 edges should be there. Without cycle. Let me try. Without cycle, 3 edges. Let's see this one. 1, 2, 3. Right? To this graph, I took one subgraph where all vertices are there, V minus 1 edges and no cycle. See, no cycle also. Can you help me now? So, to this graph, that is the one spanning tree. This is also one more spanning tree. This is also one more spanning tree. I am thinking, but try to remember. It is not a spanning tree. It is a spanning tree. For the given graph, it is a spanning tree. It is also a spanning tree. But it is not a spanning tree. Some people are asking, why it is not a spanning tree? Why? What is the answer? 4 vertices are there. It's okay. 4 minus 1, 3. 3 edges are there. That is also okay. And no cycle is there. That is also okay. But the interesting thing is, it is not a spanning tree. The reason is, it is not a subgraph of given graph. Try to remember spanning tree means a subgraph S of the given graph G is said to be a spanning tree. It may be spanning tree but not for this graph. Please be careful because in the original graph B to C edge not there, but from where this edges came. It is looking like a spanning tree. It may be spanning tree to some other graph, not for this graph. To this graph, it is not a spanning tree because this is not subgraph of the given graph. Please be careful. So, to this graph, it is a spanning tree. It is also a spanning tree. It is a spanning tree not for this graph, for some other graph. Please be careful. It is not spanning tree. Some people will think that all vertices, V minus 1 edges and no cycle, it is a spanning tree. No. It should be a first of all subgraph. If anyone said it is a spanning tree, right, to which graph it is a spanning tree? Because it is not subgraph of given graph. So I think now let's go back to the definition. Let's see once. See the definition. A subgraph S of the given graph G is said to be spanning tree if and only if S should contain this one subgraph. S should contain all vertices of G. S should contain V minus 1 edges where V is number of vertices. S cannot contain cycle. Please be careful. And one more subgraph. V minus 1 edges. no cycle. So this is the story. Can you say simplest way? Simplest way. What is the meaning of spanning tree? A subgraph of the given graph is said to be spanning tree if and only if. What is the answer? Right? So it should contain all vertices, and one more thing is with the minimum number of edges you have to cover all of them. When you say minimum, cycle cannot be there. When you say minimum, v minus 1 edges are more than enough. I think this is the spanning tree definition. I am thinking that you are really comfortable, right? Let's see next problem. Assume that this entire story, assume, right? Example 1. This entire story, assume example 1, right? Let's go to the example 2. Let's go to the example 2. See the example 2. See everyone? A, B, C, D. A, B, C, D. Right? It is a given graph. Example 2, it is a given graph. Can you help me now? To this graph, how many spanning trees are there? Find out. How many spanning trees possible for this? How many spanning trees possible for this? Please check. How many spanning trees possible for this? To this graph, how many spanning trees possible? It is there in one of your previous paper. Spanning tree definition also you know. To this graph I am asking, you don't draw whatever way you want. To this graph, how many spanning trees possible? Means all vertices, you have to take subgraphs only. First of all vertices should be there and v minus 1 edges. Can you see how many vertices? 4. 4 minus 1, 3 edges. 3 edges only you have to take. Let's see the answer for this. See the answer. I am writing the answer. See the first one, A, B, C, D. And one more thing, mostly you have to do manual checking only, mostly. You have to use brain. Instead of following some procedure and all, you have to use brain. Mostly using brain. You have to use, as a CSE person, you have to use brain. Can you help me now? How many spanning trees for this graph? Let me write one. One spanning tree. See this one? One spanning tree. This may be the one spanning tree. One. Check. All vertices, v minus 1 edges and no cycle, and one more, it is a subgraph also. Please check. One more, A, B, C, D. I think same story. What is the answer like this? Like. Check properly. If I am wrong anything, please take care. Next one more spanning tree. A, B, C, D. See this also. A, B, C, D and like this. So sorry for that. This is not there. It is not a subgraph like this. It is also a spanning tree. All vertices are there. V minus 1 edges also and no cycle. Some people are asking, sir, it is a cycle. Some people are thinking that it is a cycle. See this one. Some people are checking like this one, right? Like this. It is a cycle. Here no one there. Please be careful. It is looking like a cycle, but here no one. If anyone thinking still doubt, right? Nothing there. So you can go like this. Meaning wise same. So C to B edge there. Because of edge crossing there, you are thinking cycle there. So it is not a cycle. Please be careful. These are the small mistakes which will happen in the GATE exam. Please take care. Next one more thing. A, B, C, D. Same way. A, B, C, D. What is the answer? Just cross like this and here. If you think because of crossing, if you think some problem there, just come from outside. It is also a spanning tree. Can you help me for the given graph? How many spanning trees possible? I think 4 possible. Please check. How many spanning trees possible for this graph? How many? 4 possible. So application, see this one. Next application of greedy technique is going to be minimum cost spanning tree, which is very, very important. That is the reason I started from. What is the spanning tree definition? Yes, I given. Next one. What are the examples? For this graph, how many spanning trees possible? 4. 4. Next one. Let's go to the next one. One more example. A, B, C and D. Right, to this graph. Right, how many spanning trees possible? How many spanning trees possible? To this graph, how many spanning trees possible? We have to find out. Try. Until now 2 problems I done, right? This is the third problem. Please try this also. Manual checking I am doing. Please try to learn meaningfully. If any procedure is there, I will say that also. Just to do manually. First to try manually. When you are able to do manually, if any procedure is there, some other advantage you will get. First you learn manually doing how. Whenever any procedure is there, I will say that also. But if I say directly that procedure, you don't know what is going on. How many spanning trees possible to this graph, right? Let me write. First try to learn, right, doing manually. See this one, A, B, C, D. Right, A, B, C, D. So let me try. See this one, how many spanning trees possible? So what I will do is, see this one, what I will do is, without taking this middle line, let me write. Can you help me now? Is it spanning tree? 4 vertices are there, I took call. 4 minus 1, 3 edges. See, subgraph also. Can you help me? Is it spanning tree or not? Yes, it is a spanning tree, it's okay. But if you rotate this one with 90 degrees, right? What will happen? I think here gap will go, here gap will come. 90 degrees, just rotate like this. If you keep on rotating, what is the answer? 4 spanning trees possible. Please check. For this graph, this is the one spanning tree, I am okay. But if you rotate this one with 90 degrees, ear gap, next ear gap, next ear gap, next ear gap. If you rotate, 4 spanning trees will come. So from now onwards, you please learn, right? How to get, if anyone asks how many spanning trees possible for the given graph, don't draw one by one. If possible, bring many at a time. Concentrate that also. Until now, I drawn one by one. It's okay. Now, just concentrate that area where many will come, right? If you want many at a time, concentrate on cycles, concentrate on loop, then you will get many. So, for the given graph, right, I think 4 spanning trees I written, right, already, and one more. Until now, I have not taken care of this. With this, I may get few more. Please see here, A, B, C, D. With this, I can get few more. I am trying. A, B, C, D. It is compulsory. Right? This is one. One more, A, B, C, D, that is fine. This is compulsory, this may be. Next one, this is also A, B, C, D. Let me check this also. This is compulsory, maybe this. Next one, A, B, C, D. If really required, you can write like this one, right? If something is coming at a time many, just bring it. See this one, instead of writing 4 diagram, in one diagram only 4K. One more thing, this may be same, right? Maybe same thing like that. Please check. I think this 4 plus 4, how many? 8. Please check if anything extra possible. 8 spanning trees. For the given graph, 8 spanning trees possible. If anything missing, please check. So try, please first of all try to learn manually. Manual learning is really important. Manually you are doing means you are using brain. Manually you are doing means you are using brain. Please be careful. Afterwards some procedures may be there. We will do that also. Right. Let's go to one more problem. See the next example. A, B, C, D and E. Right. So to this problem, see this one, to this graph, right? Next example, to this graph, how many spanning trees possible? Let me try manually. Afterward, there is one nice procedure, I will say that also. Right? To this graph, how many spanning trees possible? Right? But one more thing you have to understand. Try to concentrate on those areas where many will come. How to bring many at a time? Manually, if you keep on doing one by one, it will take a lot of time, right? How to bring at a time many spanning trees, right? Let me try this, many spanning trees. Let me try one see this one. Interesting answer. A, B, C, D. At a time, how to bring many? Because if I done many times this problem, by seeing this one, I may get idea. But when you are doing new problem, you have to use those ideas. If you think that to me it is difficult, for all the people it is difficult. Please try to remember this. Right? To this one, my goal is finding number of spanning trees. I can do manually one by one. You cannot write 20 diagrams manually one by one. Try to bring at a time many. If one or two missed out, manually you can write. So how to bring many? Let me try this one. If you want many, concentrate on the loop. See this one. This is also loop. This is also loop. So concentrate on the loop so that you will get many. See this one. See interesting answer. See interesting answer. So forget about this vertex. I got this idea, right? Forget about this vertex. See this one, right? A, B, C, D. Can you help me now? With 4 vertices, is it spanning tree? With 4 vertices, it is spanning tree or not? Forget about this vertex. I will cover that also. Right? With these 4 vertices, it is a spanning tree. Rotate with 90 degrees, 90 degrees, 90 degrees. I think 4 spanning trees will come. But one thing, right? To this graph, if you want spanning tree, E also required. So with these 4, this is a spanning tree, it's okay. But E is missing. So here 4 spanning trees coming. For all these spanning trees, try to remember, E is there outside. To that E, this is the edge. Right? E is covered like this. That is fine. Right? But here 4 things are keep on rotating. I think 4 spanning trees came. Right? And one more 4 came. What is that one? You got to know. A, B, C, D. A, B, C, D. Right? I think by rotating this one with 90 degrees, I will get 4 spanning trees, it's okay. Now E, right? Like this. One more 4 will come. See, do you believe or not? At a time 8 came. For the given graph, how many spanning trees are there? I don't know the answer. My concentration here is how to bring many at a time. If you want many at a time, please concentrate on the loop. If you concentrate on the loop, you may get many at a time. Some people are asking, sir, can't I concentrate this entire area once? You can concentrate. It may give maybe 5, but I given 8. Concentrate on the many loops. If you concentrate on many loops, you may get many. If you concentrate on the larger loop, maybe you will get 5. So I concentrated on the same loop twice. I concentrated. Same loop. I concentrated. So see this one, same loop I concentrated, either these or these. With this 4 came, with this 4 came. But interesting, I think I will get few more. Why? I think in no spanning trees is one. 8 spanning trees are there. Nowhere these 2 edges are there. In every spanning tree, either this there or this one there. But no spanning tree I seen where both are there. I think based on that, few more maybe I will get. See this one, A, B, C, D. A, B, C, D and E. These 2 are compulsory. I think this may be one spanning tree. Next one, A, B, C, D and E. This will be as it is. I think this may be one more spanning tree. Check. Next one, A, B, C, D. See, one or two things, 1 or 2 missing things you can cover like this manually. Right? You cannot write everything manually. Please be careful. So I think 8 I written directly. I think 3 people are missing. I written like this. Total how many? Total I think 8 plus 3. Total I think 11 spanning trees. 11 spanning trees. Right? Please be careful. Everything is manual checking. Here our concentration. Through manual checking how to construct the spanning trees. But while doing manual checking how to construct spanning tree, don't construct one at a time. Try to bring many at a time. Means concentrate on the loops. If at all smaller loop is there, bigger loop is there. Maybe concentrate smaller loop so that maybe many will come. So for the previous problem, what is the answer? 8. To this problem, 11. Before that, 4. All I done manual checking only. All I done manual checking only. Right? Fine. Okay. I think you got some idea. That is fine. Indirectly, directly, I want to say to you, concentrate on the loops. Fine. See the next one more. Just there is one theorem to find out the number of spanning trees for the given graph. I will say now. It is very easy. I will say now. Worst case, you can use this theorem. It may take some little bit time extra. When you feel that manual checking not working from your side, 1 or 2 small mistakes are happening, right? Maybe you can use this. One example, let me explain. See this one, A, B, C, D. Carefully listen, A, B, C, D. I think to this problem already we done. How many spanning trees? This problem already you done. How many spanning trees for this one? If you want, I will show this. This problem already we done. I think this. Same problem. How many spanning trees? I think 8 spanning trees. To this problem, answer should be 8. Let's check whether we will get 8 or not. Let's see this one. Using this theorem, how many spanning trees for this we will calculate. I am doing now. I am doing. Let's see. See the first step. See the first step now. Using Kirchhoff theorem, Finding number of spanning trees for the given graph. First step is going to be, right? First step is going to be write adjacency matrix first. For the given graph, write adjacency matrix. Write adjacency matrix for the given graph first. Assume that adjacency matrix A is equal to, for the given graph, can you see how many vertices are there? 4. Let me give labels. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. First write adjacency matrix, right? What is the meaning of adjacency matrix? Two people adjacent, keep 1, otherwise keep 0. What is the answer? 1, 1, 0. What is the 1, 2? What is the 1, 2? 1. What is the 1, 3? 1. What is the 1, 4? 1. What is the 2? What is the 2, 1? Because of it the undirected, 1, 2 there means 2, 1 also there. 2, 2, 0. 2, 3? 2, 3? No. 2, 4? Yes. Go to the 3. 3, 1? Yes. 3, 2? No. 3, 3? No. 3, 4? Yes. Go to the 4. 4, 1? Yes. 4, 2? Yes. 4, 3? Yes. 4, 4, 0. That is the first step. Write adjacency matrix for the given graph. For the given graph. Yes, I written. Right, I written. See the second step. See the second step. In A, careful listen. In adjacency matrix A, see this one. In A, replace, carefully listen. In A, replace all diagonal values by its degree. In A, replace all diagonal values by its degree and all non-diagonal values once, all non-diagonal values once, replace by -1. In A means adjacency matrix. In adjacency matrix, replace all diagonal values. Diagonal values, what are those? Zeros. By its degree and all non-diagonal values once, replace by -1s. Replace by -1s. What is the meaning? I will explain. What is the meaning? I will explain. See this one. In A, let me write the A first. 1, 2, 3, 4. 1, 2, 3, 4. In A, replace all diagonal values zeros by its degree. Can you help me one small line now? What is this one? Diagonal value 1, 1. 1, 1 means vertex 1. This is 2, 2 means vertex 2. This is 3 means vertex 3. This is 4, 4 means vertex 4. Please be careful. 1, 1 means, what is the meaning? Vertex 1. 2, 2 means vertex 2. 3, 3 means vertex 3. 4, 4 means vertex 4. Please be careful. Right? We have to replace, we will replace. Next one. All non-diagonal values once, replace by -1s. Right? Now I will do this. If anyone having small doubt also, I am doing now. See this. See correctly? See correctly now. In this adjacency matrix, you have to apply this rule. What is the rule? Let me check. Can you help me? What is the 1, 1? 1, 1 is 0, but one thing, it is the diagonal value 1, 1. It is a 0. Right? It belongs to vertex 1 or not? See the graph and talk. See the graph and talk. Right? Vertex 1. What is the degree? 1, 1 means vertex 1. What is the degree? 3. Just keep 3. 0 by. Can you say what about 2, 2? 2, 2. What is the answer? 2, 2 also 0. But in the graph, vertex 2 degree 2. Go to the 3, 3. 3, 3. 3, 3 also 0. But what is the vertex 3 degree? I think 2. Next one. 4. Next one is going to be 4, 4. That is also 0. What is the fourth degree? 3. Right? Like this. Replace all diagonal zeros by its equivalent degree. Yes, I done. Next one. Replace all non-diagonal ones by -1s. Can you help me now? Right? What is the 1, 2? 1, 2. 1 is there. Is a non-diagonal value? Yes. Replace 1 by -1. What is the 1, 3? -1. What is the 1, 4? -1. Go to the 2, second row. 2, 1, -1. 2, 2 already there. 2, 3. 0 means no problem. Non-diagonal value 1 is there. Replace by -1. Go to the 3. Right? 1 means -1. 3, 2. 0 means no problem. 3, 3 already we written. 3, 4, -1. Go to the 4. All non-diagonal values once by -1 you have to replace. Yes. Right? Like this. Right? I think I am repeating once again. In adjacency matrix A, replace all diagonal value zeros by its equivalent degree and right all non-diagonal values ones replace by -1. Right? So if you do that, that is the second step. I think you got second step also. See the third step. See the third step. See the third step. Number of spanning trees is equal to cofactor of any element. Cofactor of any element. Right? Let me write now for clarification. Assume that it is a after modification, assume that a dash. So, number of spanning trees is equal to cofactor of any element, cofactor of any element of a dash, cofactor of any element of a dash. Right? Some people are asking, sir, what is the meaning of this one, which is equal to, let me find out, some element, cofactor of a dash 1 1, right? Let's find out, which is equal to, what is the meaning of this one, that row, that column we have to eliminate, a 1 1, first row, first column, this one cancel. What are the remaining people? 2 0 minus 1, 0 2 minus 1, minus 1 minus 1 3. To this one we have to find out determinant, that is the meaning of cofactor, right? So answer is going to be 2 into that row, that column remaining 6 minus of 1. Next 0 into anything is 0, that's okay. Next, right? So I think after this is the negative, this will become positive. So means same, minus 1 into that row, that column cancel. What is the answer? 0 plus 2, which will goes to, what is the answer? This will goes to 10. It will goes to minus 2, which will goes to 8. So 8 spanning trees. So this is the procedure. What is the name of this method? Name of this method is going to be, right, Kirchhoff theorem. Right, Kirchhoff theorem. Okay, sorry for that. So just cancel it. So you want to find out cofactor of any person. I think A11, that row, that column cancel. For the remaining thing, find determinant, you will get. Any element you find out, right? So I think if you want A11 also okay, A41 also okay. Right? Next one is going to be A44 also okay. You plan whatever way you want. Find cofactor of any element of A dash. So cofactor of first row, first column is equal to cancel that row, that column, whatever is pending, right? For that you find out. This is the procedure. Right? See the first step, adjacency matrix you should write. Next, in adjacency matrix, all diagonal elements replaced by its equivalent degree, non-diagonal elements once replaced by -1, zeros are zeros only. Zeros are zeros only, right? Ones by -1s. Afterwards, find cofactor of any element. If you do that, you will get the number of spanning trees. This is the way how to find out number of spanning trees. Manually, right? Manually you check. If you feel manually fine, go ahead. If you think there is some doubt also there, then go for this method. Right? Fine. That's fine.